Hello. So today we're going to be talking about electron configuration. Electron configuration is a really big part of chemistry. So what I've done is I've broken these down into about 3 or 4 separate videos. That way we can kind of piece together what electron configuration is in a more cohesive way. So today we're going to focus on what's called quantum numbers that are related to electron configuration. So an overview of what electron configuration is in general. It's a written description of how electrons are arranged in respective atoms. The electron configurations can be used to describe neutral atoms, ions, isotopes, so on and so forth. I mean, isotopes is a difference in neutral, and difference in neutrons. But also, if there is an isotope that is also an ion, you can do that too. So again, electron configuration is just to focus on the electron movement, but it can be further to describe isotopes that have already gained or lost neutrons that also have a different electrical state. It can be considered an element's address on the periodic table. I'll kind of dive further into what that means in the next couple of videos as well, but if you hear me say element address, I will refer to as electron configuration. Electron configuration is the key to understanding and predicting chemical behavior. The electrons that flow between atoms is what determines how bonds form. So if you know where those bonds are forming energy-wise and how many electrons are going where, then you can not only determine what type of bonds are formed, but you can predict what's going to happen in a chemical reaction before it even occurs. Which is a huge thing because, chemists nowadays especially don't want to start mixing chemicals all willy-nilly and then stuff's going to blow up. That we've learned from our past mistakes on not to do that. So this is a big thing in regards to experimentation, is that especially if I'm giving you a lab and I give you a chemical equation with certain elements and stuff, hopefully by the end of the first semester, you'll have a general idea. It's like, okay, this compound reacts in this way, which means this is going to do that, and so on and so forth. It can be used to determine reactivity, types of reactions, size of atoms, and other electrical properties of elemental atoms as well. Electron configuration is composed of 4 different quantum numbers. Okay, so the principal quantum number, the orbital quantum number, the magnetic quantum number, and the spin quantum number. That's what we're going to focus on in this video, is kind of describing what those 4 kind of really deal with and how they represented on the periodic table to start beginning how to read that periodic table successfully. So the principal quantum number, it's the numerical identifier of the electron energy level, as well as the most probable distance that the electron is from the nucleus. So going back to the Bohr model, each of those orbits is assigned a principal quantum number, 1, 2, 3, 4, so on and so forth. And that principal quantum number, or that principal energy level, is what tells us where that electron relatively is and how much energy is within that itself. Excuse me. It consists of a number 1 through 7 so far. There might possibly be a number 8, depending on if we discover any new elements here in the next couple of years or so. But as of right now, it's just 1 through 7. 1 meaning it's the closest to the nucleus, so that closest orbit to the nucleus has the lowest energy, and then 7 farthest from the nucleus, which means it has the highest energy. It also corresponds to the periods or rows on the period of the elements on the periodic table. So periods are the rows if you read across from left to right on the periodic table. So if you hear me refer to the periods on the periodic table, that's what I'm referring to. It's just the rows, individual rows of the elements itself. So we'll kind of break this down. So if you ever look at a periodic table, you actually might notice that there's a couple of numbers off to the left-hand side. This 1 through 7 determines the energy level. So, for example, hydrogen and helium have electrons only in the quantum number 1 energy level. But if I go down to like iron, it has electrons in the 4 energy level, the 3 energy level, the 2 energy level, and the 1. Because for every proton that you add as you're reading across the periodic table to get to iron, you also have to add electrons to keep it neutral. So you are gaining electrons, and as you gain more electrons, they have to spread out further into different energy levels. So that's the first portion of how to read this with electron configuration. Next one is the orbital quantum number. This one's a little bit more funky, kind of. It indicates the shape of the electron sublevel or orbital of that electron that is present in. So earlier in the quantum theory video, I briefly kind of showed you what the shapes of these orbitals could look like and what these electrons, where they could be at. So each energy level has different shapes, and we assign these shapes quantum numbers in the form of letters. So the letters can be either S, P, D, or F. Okay. So the way this works is I want to set this up in a graph form. So if it's set them up S, P, D, and F in a more linear order, and I make a notation of increasing distance from the nucleus to increasing energy of electrons, we can say that as you go up in letters or go from S to F, the distance away from the nucleus pretty much increases. For the context of this class, that's true. As you go on to further academic career in regards to chemistry, in chemistry and physics, there are instances where that's not necessarily true, but for the general basic concepts that we can use to predict atoms in this class, we are going to just assume that's true and not worry about it. If you have any questions about that, come talk to me. I'm more welcome to talk to you more about that. Increasing energy of electrons too. So as we go further higher up into the orbital quantum numbers, we know that those electrons are getting further from the nucleus, which means that they're also increasing in energy as well. So the way this is kind of broken down, this is kind of, I'm going to try to break this down into shapes and colors. So if you have an empty periodic table that I may have given you in class, or one that you want to print off, or anything like that, feel free to do that. That way you can kind of start shading this stuff in to indicate where these orbitals are present. And as you're reading the periodic table, you know what the ending orbital or what orbitals are included in each element's address on the periodic table. So the S orbitals I'm going to illustrate in blue. So everything on the left-hand side of the periodic table are s orbitals, okay? At least this is where their electrons end. So this is beryllium, I believe. So if I was doing an element's address for beryllium, I would know that the last electrons in beryllium that I would account for would be in a 2s orbital. So this 2 is the quantum number, the energy level, and what that orbital is at. So they'd be in a 2s orbital. The s orbitals also go over to helium. So 1s actually gets stretched out. The reason why is because helium is actually a noble gas, so they wanted to put it over here on the right-hand side. But it actually falls within the 1s orbital. So H has a 1s orbital only, and then helium has a 1s orbital only. Hydrogen has 1 electron and the helium has 2. And that goes back to the Bohr model. If you remember in the last video, I told you that the first orbit only has 2 electrons. This is the reason why, is because that first orbital, this s orbital, can only allow 2 electrons to be in it. That's the reason why helium's over here in the noble gases, and it starts over the 2s orbitals down here. So the p orbitals, I'm going to notate in yellow, is this big, huge block over here. So the way you would read this, you would go 1s1, 1s1, 1s2, 2s1, 2s2, and then you jump over here, and since the 2 is still on this row, you would go 2p1, 2p2, so on and so forth. And that's how you would kind of read that across the periodic table. I will illustrate this further in class if it's not making a little bit of sense right now, so don't worry about it. But I'm just trying to give you the basics of what this is. D orbitals are going to be notated in green. It's the transition metals, the middle of the periodic table are the d orbitals. So the d orbitals are stretched 10 across, and so the way you would get down to here, you say 4s1, 4s2, then you get into your d's, and then you get into your p's over here as you're reading back across. And lastly, the f orbitals. This is for the rare metals. These are the ones that act funky or highly radioactive and everything like that. They're these bottom 2 rows right here. Now, these bottom 2 rows actually do fit into the main portion of the periodic table right here, but I'll dive further into that in later videos. But we take them out because these are the only 2 rows within the periodic table that have these f orbitals. Okay. So the magnetic quantum number indicates the position of electron orbital in 3D space. And so these are the type of orbitals that are possible to be known. So s orbitals are these sphere-looking orbitals right here. There's only one type of sphere that you can have, so therefore there's only one position that these electrons can be in, or one type of shape that these electrons can be in when it's at an s-level orbital. So that's the reason why the possible electron positions is only 1. Then you get down to p. A lot of people call these the dumbbell orbitals, you know, the things that you lift weights. They can be in 3 different positions. So there's one that's along the x-axis, there's one that's along the z-axis, and there's one along the y-axis. So there's actually 3 electron positions that are possible. Electrons can be in either of these 3 types of p orbitals. Then d orbitals have 5, and they have weird looking shapes. They're kind of hard to describe, but there are 5 different types of d orbitals that electrons can occupy. So they have 5 technical positions that electrons can appear in. And then you get down to f, and they're even more funky, and they have 7. So there's possible 7 electron positions that electrons can be in f orbitals. Spin quantum number. This is a little bit easier. Indicates the direction of how the electron spins. An electron spin is either clockwise or counterclockwise. Now, clockwise in 3D space and counterclockwise in 3D space. But when we draw it two-dimensionally, it's a little bit hard. So the way we kind of describe this is spins are given numerical values of either +1/2 or -1/2, and I'll describe why here in just a second. So this is an electron orbital position. This would be like a magnetic quantum number. And up arrow means a clockwise turn, okay, which means we give it a magnetic or a spin quantum number of 1/2, +1/2 if it's spinning up. But then if I take the same orbital and I turn the spin down, then it becomes -1/2. That means that the electron is spinning in a counterclockwise position. But if I have 2 electrons occupying this orbital, and I have one going up and one going down, then it has 0. So those electrons are canceling each other out in regards to neutrality. Now, for all our electron configurations within this class, if you have 2 electrons occupying one orbital, there's always going to be one going up and one going down. Okay, there is a possibility that electrons can both spin up and spin down, but those are what's called microstates, and that is advanced chemistry. So whenever you write electron configurations in my class, if there is 2 electrons in one orbital, one always has to go up and one always has to go down. So we kind of start breaking this down a little bit further. So the way we start labeling these is, like I said, 1s for hydrogen, 1s for helium as well, because it just breaks off because it wants to be part of the noble gases. These 2 blocks are going to be, their ending addresses are going to end with 2s, 3s down here, 4s, 5s, 6s, 7s. And then you have 2p, 3p, 4p, 5p, 6p, 7p. So if there's any elements that we're trying to do, their element address will end in whatever these are. Then you get to the Ds. The Ds are the ones that start getting weird. So if you notice, if I'm reading left to right on the periodic table, I'll go 3s, 3p, get a 4s, and then I go 3d. So I drop down in a quantum number, a principal quantum number, an energy level. And so the reason why is how these orbitals arrange themselves within the atom. Based on the D configuration, the electrons want to occupy a lower state than it is at the S orbital. So when you're reading across the periodic table, this is where it starts becoming tricky. So again, if I was going for like iron, which is around here, and that's FD5, 3D5, excuse me. So I would read it as 3P6, 4s2, because there's 2 blocks here, and then I would go 3d 1, 2, 3, 4, 5. Okay, so it end with 3d5. And then when you get through the d's, then you jump back up to 4p. So you need to start identifying that d's start one less than the quantum number that's to the left of the periodic table. Okay, so if I keep going further down, 5s, and you go to 4d, 5p, 6s to 5d, 7s to 6d. F's are even weirder. F's, they start at 4f, okay? But oddly enough is that this 4f is actually stuck within the 6th row of the periodic table, and again, I'll dive further into what that means in other videos. So what will happen is that when you go to read around 6 and also 7, they start off 2 less than what the principal quantum number is. So you would actually read 6s, and then it would be 4f, and then 5d, and then 6p, and then 7s, and 5f, 6d, 7p, so on and so forth. All right, so that's kind of the end of this video. I know it's kind of a lot of information, but that's kind of breaking down the basics of electron configuration. Again, if you have any questions, please feel free to come and talk to me or email me or anything like that. I'd be more than kind of go more step by step with you, and I'm sure I'll review this in class in the days to come. So thanks for watching this video, and I hope to see you next time.